Hello, my name is Georgiadis, and I'm here to present my paper, Optimal Feedback in Contests. This is joint work with Jeff Ely of Northwestern, Sina Khorasani of UCSD, and Luis Rayo, also from Northwestern. Contests, situations in which agents compete for a prize, can be an effective way to organize economic activity. For instance, labor market tournaments, innovation contests, all-pay auctions, legal and political battles, as well as athletic events, all share these features. Now, contests are inherently dynamic, and in many situations, the designer has an informational advantage over the participants about how they're doing mid-contest. In this paper, we are interested in optimal dynamic contests when the designer chooses when the contest ends, how a fixed prize is to be allocated, and a real-time feedback policy. Now, as an example, consider a promotion contest. Specifically, imagine a firm that wants to promote one of its associates to a VP. It has one open slot and several candidates. The firm monitors effort imperfectly, and it is arguably better informed than the associates themselves about their performance. So how should a firm design a contest in this situation to motivate their associates to work hard? This is one of the questions that this paper aims to address. As a second example, consider innovation races. Specifically, think of the 2006 Netflix prize, where Netflix promised a $1 million prize for an algorithm that could predict user film ratings with at least a 10% better accuracy than Netflix's own algorithm at the time. So what is the best way to design the rules of such a contest? In the interest of time, I'm going to skip the literature review and jump straight into the model. So in terms of players, we have a principal and N agents. The timing of the game proceeds as follows. So at the start of the game, the principal designs a contest which comprises of three objects. First, a rule that specifies when the contest will end. Second, a rule for allocating a fixed price whose value we normalize to $1, and a real-time feedback policy. At every moment thereafter, each agent receives a message in accordance with the feedback policy and chooses whether to work or shirk. And working is costly. When the contest ends, the prize is awarded according to the allocation rule, payoffs are realized, and all players go home. Each agent's effort generates a binary signal, which takes the form of a Poisson success. That means that conditional on not having succeeded by some time t, an agent succeeds during the next interval of length dt with probability that is equal to his effort times dt. And here we normalize the hazard rate of success to 1. That is to say that the hazard rate is constant. Later in one of our extensions, we consider the case in which the hazard rate is increasing in past efforts. And this will allow us to capture a notion of progress or knowledge accumulation. Now, who observes what? The principal observes successes, but not efforts. And that is to say that the principal faces a moral hazard problem. The agents do not observe their rival successes, and each agent may or may not observe their own success, or may do so probabilistically. So depending on which application you have in mind, a different assumption may be more suitable in this situation. For instance, in the case of a promotion contest, it is conceivable that agents don't know, at least not definitively, whether, for instance, they have met a promotion bar. On the flip side, in the context of an innovation contest, now it is more likely that agents do observe their own successes. Now, let me elaborate on the principal's choice variables. So remember that the principal is choosing three objects. The first is the termination rule, which formally is a stopping time with respect to each agent's success time. So as an example, the contest could end at a pre-specified deadline. It could end upon the first success, and so on. The second object is a prize allocation rule, which specifies each agent's share of the prize, which we denote by QI, as a function of when each agent succeeds. So as an example, the prize could be awarded to the first agent to succeed. It could be awarded randomly, or of course, you can envision more complex allocation rules. Finally, the feedback policy specifies the message that is sent to each agent at every moment in time as a function of the agent's success times and past messages. So, for example, the principal could give random feedback. She could give private or public feedback. She could give feedback about one's own or about other successes, feedback about feedback, and so on. We don't impose any restrictions on the termination rule, the prize allocation rule, or the feedback policy. For any given contest, each agent's expected payoff is equal to his expected share of the prize less his expected cost of effort. So remember that QI is the agent's share of the prize, and C is the agent's marginal cost of effort. We assume that the marginal cost of effort lies between 1 over n and 1. Now, if the marginal cost of effort were to be bigger than 1, then it would be impossible to ever incentivize the agent to work. That is because the value of the prize and the hazard rate of success is equal to 1. On the flip side, if the marginal cost were to be smaller than 1 over n, in that case, the principal would be better off contracting with each agent individually rather than using a contest. Now let's turn to the principal's objective. The principal designs a contest to maximize total effort. That is, she wants to choose the rules of the contest and a set of effort profiles so as to maximize effort subject to 2 constraints. The first is that these effort profiles form an equilibrium, and the second is a budget constraint, namely that the principal only has a unit of the prize to award. Now, let me just briefly remark that it will turn out that the principal's optimal contest is also going to maximize the expected number of successes, not just total effort. Finding an optimal contest in this situation is hard because the choice variables are high-dimensional objects and they can condition on the entire history. The way we attack this problem is by a sufficiency result, which gives us an optimality guarantee. Specifically, a contest is guaranteed to be optimal if in equilibrium 2 things are true. First, it awards the entire prize with probability 1. And second, if each agent earns 0 rents in that contest. Now, to see why this is the case, notice that the principal's objective, which is the sum of the agent's efforts, can be rewritten in the following form that you see in this display equation. Specifically, it can be written as total surplus minus agent rents. And to write down this expression, we're using the each agent's expected payoff function. Now, the total surplus is, of course, bounded from above by 1 because the principal has a unit of the price to give. And the agent's rents are bounded from below by 0 because each agent can guarantee himself a 0 payoff by not working. Now, of course, if a contest attains those bounds, it has to be optimal. And in that situation, the principal's payoff is going to be 1 over C. Now, before I show you the main result, I have to give you some definitions. So first, I'm going to define a termination rule, specifically for some capital T star, which I will characterize later. Let's define the termination rule tau star, in which allows the contest to run in cycles of length T star, and the contest is terminated at the end of the first cycle in which at least one agent has succeeded. Second, I'm going to define the egalitarian prize allocation rule to be the one which shares the prize equally among all agents who have succeeded, irrespective of when they happen to do so. Because the agents are risk neutral, equivalently, this allocation rule can award the prize to each agent who succeeded with equal probability. Finally, I'm going to define the feedback policy en pronto. And this feedback policy is going to keep agents fully apprised of their own success. Now, let me show you the main result. And this result states that the contest with termination rule tau star, the egalitarian prize allocation rule, and the feedback policy en pronto is optimal. In equilibrium in this contest, each agent works until he succeeds and earns no rents. He works until he succeeds because as soon as he succeeds, the principal informs him so, and at that moment, the agent optimally stops working. This contest is optimal because it meets the criteria of that key lemma. Specifically, it awards the prize with probability 1, since the contest ends only after an agent has succeeded, and the egalitarian allocation rule, together with the M-Pronto feedback policy and the cycle length T star, ensure that agents are kept indifferent between working and shirking at all times, and they earn no rents. Now, let me explain how the ingredients of this contest come together to give us the desired result. First of all, if you want to design a contest that extracts all rents, the feedback policy has got to be M-Pronto. That is because if the principal were to use any feedback policy that keeps agents in the dark about whether they have succeeded, they could halt effort for a short amount of time, thereby becoming more optimistic that they have not yet succeeded. And that would make effort more worthwhile, and they would be able to extract rents. As a reminder, here the principal values effort even after an agent succeeds. So in a way, the principal is shooting herself in the foot with this feedback policy, because as soon as an agent succeeds, it tells the agent stop working effectively. Second, in order to give no rents to the agents, it has got to be the case that each agent's expected reward, conditional on succeeding at any moment t, has to be equal to his marginal cost. And this has to be true for all agents and for all times. Now, the egalitarian prize allocation rule uniquely provides such symmetric and time-invariant rewards. That is because by definition, each agent reward is the same irrespective of when he succeeds, and it's also symmetric. The cycle length is able to scale the reward by affecting how many contestants a successful agent is going to have to share the prize with. Specifically, my expected reward conditional on succeeding at any moment depends on how many of my rivals I expect to have to share that prize with. If the cycle is short, if I succeed during a given cycle, I expect to only have to share the prize with a small number of agents. So my expected reward is going to be close to 1, which is the size of the entire prize. On the flip side, as the cycle length increases, even if I succeed, I expect that I'm going to have to share the prize with several of my rivals, which dilutes the prize. What we show is that by choosing the cycle length and setting it T star, we can make that expected reward exactly equal to C, thereby extracting all rents. Finally, the cyclical structure ensures that the contest ends only after at least one agent has succeeded, thereby ensuring that we award the entire prize with probability 1. Now, let me give you some remarks about the optimal contest. First of all, this contest would remain optimal even if agents could observe their own successes directly or did so probabilistically. That is because the optimal feedback policy M-Pronto keeps agents fully apprised of their own success. Second, because the optimal contest guarantees that agents work until they succeed, it also maximizes effort conditional on an agent not having yet succeeded. They're maximizing the expected number of successes in addition to maximizing total effort. Third point is that in this case, it suffices that the principal can commit to one cycle at a time. That is, the principal does not have to commit to the entire contest at the outset. That is because as soon as its cycle ends, it's in the principal's best interest to start a new identical cycle. Recall that the principal observes a very coarse signal of effort. In fact, she would be no better off even if she had a more precise monitoring technology. That is because the principal is able to achieve the upper bound on her payoff, which is 1/C. Finally, a similar contest would also be optimal if the number of agents were to be random. The only difference in the design is that the cycle length T star would have to account for the agent's beliefs about the number of contestants, which as the contest goes on, that would change because the agents would update their beliefs about the number of rivals, given that nobody has succeeded so far. To evaluate the robustness of our results, we also consider a few extensions. First, if players discount time, now a new trade-off arises. Because the prize is shrinking over time, on the one hand, the principal would like to end the contest as soon as the first agent succeeds, and this would allow her to best utilize the prize. And on the other hand, she would like to extend the contest in order to extract rents. As a result, characterizing an optimal contest is difficult in this situation. Nonetheless, we show that the cyclical egalitarian design is approximately optimal when the discount rate is small, when the marginal cost of effort is close to 1, or the number of agents is large. Moreover, simulations suggest that this contest also performs well away from these limits. In our contest design, one thing that's important is that the principal can commit to a feedback policy. That is because it is in the principal's best interest to keep the agents from stopping working for as long as possible. Now, if the principal cannot resist that temptation and she cannot credibly communicate with the agents mid-contest, then the optimal contest features a deadline at which point the contest ends and the egalitarian prize and no feedback. Finally, we consider the case in which the hazard rate of success of each agent increases in past efforts. This is aimed at capturing a notion of progress or knowledge accumulation. In this case, we show that the optimal contest features an egalitarian prize and the M-Pronto feedback policy just like before, and the only difference is that cycles now have a stochastic length. This contest satisfies the criteria of the key lemma. Specifically, it awards the entire prize with probability 1 and extracts all rents and is therefore optimal. To conclude, we study a simple model in which the principal designs a contest with endogenous feedback. And we show that the optimal contest features a cyclical structure, an egalitarian prize allocation rule, and a feedback policy which keeps agents fully apprised of their own success, but informs them about rival successes only periodically when a new cycle starts. What is next? A natural first extension is to look at the case of heterogeneous agents. In this case, we have solved the 2-agent case, but extending it to n agents is hard. Another extension has to do with a case where the hazard rate is decreasing, and this can capture situations of strategic experimentation. And finally, another question has to do with a case in which the principal cannot extract all rents. Thank you.